keeps us warm. I wonder if our mission will have anything to do with that. You know, studying the sun. What questions now? The ones that expected astronauts to know.
Oh, I think questions like, how big is the sun? How old is it? How long will it shine?
What's it made out of?
How does it affect the Earth?
You know, living in complete darkness would bother a lot of people. But not this astronaut. I'm a highly trained professional.
Right.
Hey! What happened? Somebody help! Stanley!
Highly trained professional, huh?
The sun may look like it's close by, but check this out. Let's say there's a bridge that reaches from the Earth to the sun. If you drove at a constant speed of 60 miles per hour, which is 97 kilometers per hour, it would take, let's see, the sun is 93 million miles away divided by 60. That's 1,550,000 hours. 177 years. That's without stopping. For anything.
We need to get a jump on the other astronauts and find out what the sun is all about.
Wouldn't it be great if we could just hop into a spaceship and cruise on by the sun for some hands-on experience? I bet we'd get a killer tan.
Malcolm, the sun's rays can cause sunburn and even skin cancer here on Earth. And if we try to get near the sun, we try to a crisp in an instant. From Earth, we can watch our sun make a daily trek across the sky from east to west. Now we know that this apparent movement is just an illusion, but thousands of years ago, scientists believed it. They thought that the Earth was the center of the universe, and the sun revolved around it. This was called the geocentric theory.
Makes sense. After all, that's the way it looks.
It wasn't until the 16th and 17th century when great astronomers such as Copernicus and Galileo changed the way we view the universe today. They believed in the heliocentric theory, that planets, moons, asteroids, and comets in our solar system revolve not around the Earth, but around the sun.
And the sun is very big, too.
It's bigger than big. Bigger than all the planets in the solar system combined. That's why it takes Earth 365 days to go around just once.
Yeah, that's a hefty trip.
On the other hand, our sun is really just a very small part of the entire universe. After all, our sun is a star. And it's just one star out of billions of stars in our home galaxy, the Milky Way. And that's not all. Our galaxy is just one out of an estimated 50 billion other galaxies. So it makes you wonder, is the sun the only star in the universe that has a system of planets around it?
Actually, recent discoveries have found other planets orbiting sun-like stars in our galaxy. But the question remains, is there any kind of life on those planets? So far, the answer is unknown. But there's still billions and billions of other stars out there to check out, so you never know.
So our sun is a star. But even though it's pretty far away,
93 million miles, which is 150 million kilometers.
it's still much, much closer to Earth than any other star. In fact, the next closest star is 40 trillion kilometers away, which converts to...
Woo! I got it! That's about 25 trillion miles!
Our sun is considered to be a medium-sized star. Some stars are much smaller, just a few kilometers wide, and others can be 1,000 times bigger. Like all stars, our sun was formed from a cloud of dust and gas called a nebula. Within the nebula, the particles were attracted to each other, and the whole cloud began to compact until it became very dense, extremely hot, and built up enormous pressure.
Go, Nebula, go!
With these conditions, nuclear fusion takes place. This is a process where two or more nuclei of one element combine to form a different, heavier element. In the case of the sun, we're talking about the fusion of hydrogen gas into helium gas.
And what does that do?
Think of the power of billions of nuclear bombs exploding every second. This is what's happening inside the sun.
Kaboom!
Nuclear fusion results in a release of light and heat, which causes the sun to shine. Energy waves are sent out in all directions all over the universe. In addition to visible light, the sun emits other kinds of energy waves, including radio waves, microwaves, infrared waves, ultraviolet waves, X-rays, and gamma rays.
Do not attempt this at home. We are highly trained professionals wearing protective clothing and headgear.
Why are you watching the microwave oven?
I'm not watching the microwave oven. I'm watching for microwaves. The sun gives out all these powerful energy waves. Or so I've been told. I just want to see what one looks like.
But microwaves are invisible.
Oh, I guess that explains why I haven't seen anything.
Yeah, it would. But let's move on to the sun's life cycle. That's not invisible, but it does take a very long time.
Okay, but let me get my lunch first. Here we go.
It's weird to think about it, but our sun will not burn forever. Like all stars, the sun goes through a life cycle. It has a beginning, middle, and an end.
What stage is it in now?
Right now, it's in the middle of its life. It's been burning for about 5 billion years, and it should burn for about 5 billion more. Our sun is called a main sequence star. It is stable and running on plenty of hydrogen fuel. It will remain this way for billions of years to come. Of course, there will come a time when our sun's hydrogen fuel begins to run low, and the core will become unstable and contract. This process will release energy and cause the outer shell of the sun to expand, making our sun about 100 times bigger than it is now.
And I've heard that it won't be yellow anymore. It will turn red.
You heard right. This is called the red giant phase. Billions of years after that, most of the hydrogen will finally run out, and all that will remain of the sun is its core. Gravity will cause the core to collapse inward and compact. When this happens, the sun enters its white dwarf stage. It will be smaller than the Earth, about half the size of the moon, but it will still shine a hot white light. Finally, when the sun stops emitting any energy at all, it will cool down and end its life as a cold, dark, dead star. But again, this won't happen for billions of years.
It may seem strange when you think about it, but billions of years from now, when our sun becomes a red giant, it will be much, much larger. But it will only be as bright as the full moon. By the time this happens, billions of years from now, it's unlikely that any life as we know it will exist on Earth. I'll bet that because the sun is so close to us compared to other stars, we've learned a lot more about it.
Yes, Malcolm. Since the sun is made only of gases, there are not clear boundaries with it. But to help explain how the sun works, astronomers have divided it into 4 general layers. The innermost layer is the core. This is where nuclear fusion turns hydrogen gas into helium gas, resulting in a tremendous release of energy, making the core the hottest part of the sun.
What kind of numbers are we talking about?
Try 15 million degrees Celsius.
Wow!
This energy from the core travels outward to the sun's surface atmosphere, which is made up of 3 layers. The first is the photosphere. Incredibly, the temperature here drops way down to about 6,000 degrees Celsius. It's through this layer where the sun can pass out into space. So the photosphere is the only part of the sun we can see.
I can remember that. Photo means like we can see.
The next layer out is the chromosphere. Being further away from the sun's core, you would think the temperature would continue to get cooler. But not so. Temperatures in this layer rise to about 100,000 degrees Celsius.
Yes! That's odd. Why?
Great question, Malcolm. And scientists are studying it, but they still don't have a definite answer.
Aha! A solar mystery.
Finally, the sun's outermost layer is the corona. The corona extends for millions of kilometers into space. As its distance from the sun increases, its temperature continues to rise. It gets hotter than 1 million degrees Celsius. Normally, we cannot see the corona from Earth unless there's a total solar eclipse. This occurs when the moon passes between the sun and Earth and blocks out the sun. all except for the glowing corona, which can be seen. This doesn't happen very often, about once every 5 years. So as you can imagine, Malcolm, some ancient cultures used to believe a solar eclipse was a bad omen.
Well, sure. Having the sun disappear for a few minutes must have been pretty scary back then.
A solar eclipse may have been scary, but the sun was an important part of the culture of many ancient civilizations. For example, around 2,000 years ago, the ancient Pueblo people of North America, known as the Anasazi or Isatsino, used careful observations of the sun to mark the seasons, figure out when to plant crops, and to try to understand the history of the universe. Even today, the people of Peru still celebrate a festival which honors the old Peruvian sun god Inti. Core, photosphere, chromosphere, corona. Core, photosphere, chromosphere, corona. What are you doing with binoculars?
I hear our sun's a real active fireball of activity, spewing gas millions of kilometers into space. So I figured, what better way to get a closer look than with these binoculars? That way,
Timmy knows, are you crazy? You should never look directly into the sun. Not with binoculars, not with a telescope, nothing. Everyone knows you can damage your eyes that way.
well then, Stanley, how am I supposed to safely look at the sun?
So it's not high tech, but it can still capture an image of the sun. It's a pinhole viewer, and it's easy to make, and it allows you to calculate the diameter of the sun. Grab a meter stick, 2 index cards, some tape, and a pin. Tape an index card to one end of the meter stick to make a screen. Make a pinhole in the other index card. Make sure it's just a pinhole, nothing bigger. Take this index card to the opposite end of the meter stick. Now go outside and look around. Aim the pinhole card toward the sun so an image forms on the other card. And remember, you can't use this to look directly at the sun. Measure the diameter in centimeters of the sun's image on the card. Now you can actually figure out the sun's diameter by using this number. Divide your measurement by the length of the meter in centimeters. Now, multiply that number by 150 million kilometers, the sun's distance from the Earth. Did you get 1,350,000 kilometers? Good, because that's the diameter of the sun.
We know that the sun is the source of light and heat that keeps life going on Earth. But there's another side to the sun.
This sounds exciting.
Yes, within the sun are huge electrical currents that produce the sun's magnetic field. And just as 2 electrical wires will spark when they are crossed, solar disturbances occur when the sun's magnetic fields get twisted up. These magnetic storms may result in the formation of sunspots. Sunspots are darker, cooler areas in the sun's photosphere, and many may be larger than the Earth. Scientists believe that sunspots may have an effect on our weather. More sunspot activity may cause warmer temperatures on Earth. Less activity may cause cooler temperatures.
I'm intrigued. Go on.
As the magnetic storm from the sun grows stronger, the sunspots may erupt into dramatic solar flares, which can cause enormous bursts of charged subatomic particles to be ejected from the sun. Sometimes, when these charged particles collide with the particles in the Earth's upper atmosphere, they glow, producing an aurora, also known as the northern or southern lights. Another kind of violent storm of the sun is called a solar prominence, which are violent eruptions of gas. Viewed from Earth, they look like huge loops or arches. Prominences may last for several months before breaking apart. Then there's solar wind.
Not the kind of thing we're used to here on Earth.
No, this is a continuous stream of high-energy gas particles that blows off the sun in all directions at speeds that can reach 1 million kilometers per hour.
How does all this dramatic activity on the sun affect us? In addition to influencing our weather, this radiation from the sun may damage the electronics of space. Which can harm astronauts in space or satellites orbiting the Earth. And this solar activity can even influence us here on Earth by producing surges of electrical power or by disrupting radar, telephone, and radio communications. Even cellular phones and cables can be affected by the sun's activity.
Luckily, Malcolm, for years now, space agencies such as NASA and the European Space Agency have been studying the sun and its effects on Earth and its atmosphere. In the early 1970s, there was Skylab.
Oh yeah! That was the first space station, wasn't it?
Correct. Skylab carried a whole observatory with 8 specialized telescopes just to watch the sun. In the 1990s, there was Ulysses, a probe sent to investigate the sun's poles. One thing it learned was that solar wind from the poles is 3 to 4 times faster than it is from the sun's equator. This is because the ionized gas at the equator is more dense than at the pole, which prevents the solar wind's particles from escaping. Next, there was SOHO, the Solar and Heliospheric Observatory. This was a probe designed to learn about the structure of the solar interior and how solar wind is created.
So I guess for an up close and personal look at the sun, you definitely need to have technology in space.
Well, we've also got some pretty cool high-tech equipment right here on the ground.
I'm Dr. David Hathaway. I'm a solar astronomer at NASA's Marshall Space Flight Center. As a solar astronomer, I'm interested in how the sun works and how it impacts us here on Earth. The key to understanding the sun is the sun's magnetic field. The vector magnetograph measures magnetic fields on the sun by looking at the light that comes from the sun and determining the strength and the direction of the magnetic field, how they're twisted, and when they are apt to explode. This helps us to predict solar flares and prominence eruptions.
150.
Our vector magnetograph is placed up high on a platform to get above the air currents that are close to the ground. The purpose is to try to get as clear an image of the sun as you can. And currents in the air tend to cause the image to wiggle and squirm. The magnetograph consists first of a telescope that looks at the sun, forms an image of the sun, but before we form that image, we filter out the sunlight so that we only see the light due to iron atoms in the sun's atmosphere. And from that, we get information about the sun's magnetic field. The main reason I study the sun is out of scientific curiosity. I'm interested in how the sun works, how it's related to things that happen on other stars, how it impacts life here on Earth, but there's also this practical side studying the sun, learning how to protect ourselves both here on Earth and as we venture into space.
Do you realize that without the sun, these flowers wouldn't grow? Don't tell me there's a bee in your soup.
No, I just had a disturbing thought. Without the sun, our planet would be nothing but a lifeless, cold, dark rock. So I have composed this sun dance in its honor and to show my appreciation. Want to join in?
No thanks.
Although the sun is just one of billions and billions of stars, it is the ultimate source of energy for all living things on our home, planet Earth.
You're right, buddy. Energy from the sun provides our food, either directly or indirectly. Plants trap sunlight to produce food during photosynthesis.
And animals either eat plants for food or eat plants eating animals.
The sun is also the engine source that drives the water cycle. A constant cycle of evaporation, condensation, and precipitation that produces our weather.
And I guess we can thank the sun for keeping our temperatures little, right?
Actually, it's our distance from the sun. If our planet were much closer to the sun, like our neighboring planet Venus, the intense heat would burn everything around us and evaporate our ocean.